Hello and welcome to this lecture. So we're going to continue looking at some specific aspects of the matrix inverse and some algebra with it, some examples, etc. Okay. So before we get started, it's important to sort of contrast. I always like this contrast between how you divide and think of inverse of numbers, real numbers, versus matrices. So what are the differences? What are the similarities? Like it gives a sort of a mathematical notion of how things change. You're doing the same multiplication, addition, division, but then some things change when you go from numbers to matrices. What are those changes? Okay, so let's take a look at that. So if you have a real number a, we'll assume a is not 0. So if a is 0, you can't divide with it. So we'll assume a is not 0. It's a real number a. We have looked at this, multiplication being, sort of the number actually representing a transformation of the real numbers. If you remember, I mentioned this, the connection between a number and the transformation it represents. So we've been thinking of a, the number a, representing a transformation ma, which is like multiplication by a. So it takes every real number x to ax, right? So this is something we've been thinking about. So in that sense, a inverse, which is actually 1 by a, we also write a inverse as 1 by a, right? Represents multiplication by a inverse, which is what it takes x to x by a. Okay, so you divide x by a. So here you multiply x by a, here you divide x by a, and if you put these two together, if you compose these two, you get identity, right? So if you compose MA with MA inverse or MA inverse with MA, you get identity, which is how the multiplication is defined. So you take A into A inverse, A inverse into A to be equal to 1, which is the multiplication by 1, which is like the identity, right? So this is sort of a correspondence which we carried forward into the matrix world. But then some more things we can do with numbers. So for instance, this kind of idea is used in solving equations with variables. Like for instance, you may have a variable, like equation like ay equals b. Y may be an unknown. A is a number, b is a number. So what do? You multiply both sides by a inverse. You get y equals b by a or a inverse b or something like that. So this is very standard. This you must have done from a very young age in school. So you can do something similar with matrices. We'll once again start with the matrix A, which is an n cross n matrix. We'll assume A is invertible. So in this case, what does A represent? It represents a transformation from Rn to Rn. We know how to think of this transformation. A is the matrix. You multiply with the vector on the right, you get another vector. So that's how you go from vector to vector through A, right? So that's the transformation P. So A inverse, we think of it as representing T inverse, which is the transformation from Rn to Rn again. And with this, we know how to do this, right? So you can compose T and T inverse at T, you get the identity. Now A into A inverse is the A inverse into A, you get the identity matrix, right? So matrix with 1 on the diagonals, 0 elsewhere. So this is something that is used in the definition of inverse and multiplication and all of that. Okay, so this is sort of very, very similar. So I just want to show you that the way we are defining matrix multiplication, the way we are defining the inverse, sort of is similar to the real numbers. But if you think of equations, immediately you'll see there'll be one dramatic difference. I'll show you what the difference is. You'll see, so there'll be one very important notion. Supposing you have an equation, capital A into y equals b, where y also is an n by n matrix. We're thinking of an equation. You can multiply both sides on the left by A inverse. Notice immediately there is this multiplication on the left. So when you say, in this case, you don't have to qualify that. You can say multiply both sides by A inverse. You can multiply on the left or on the right, you get the same answer, y equals b by A. So here, when you multiply both sides on the left, you get something reasonable, because when you multiply by A inverse AY becomes just y, and then you get A inverse on this side. So you get this, right? So it's very clean. On the other hand, if you multiply both sides on the right by A inverse, you cannot do anything. You will just get this equation AY A inverse equals B A inverse, and you're sort of stuck. You can't simplify this. So remember, matrix multiplication is not commutative. So Y A inverse need not be the same as A inverse Y. So you can't shift this around. You have to stay with this. So this you can't do anything about. Okay. So this one property of this matrix multiplication not being commutative changes the multiplication and inverse and how you work with these things dramatically. Towards the end, we'll see some examples where this kind of a notion will become very interesting in some problems and all. Okay, so just wanted to keep this in mind, while A lot of the matrices are sort of like numbers. You do multiplication, division, all that. They are also very, very different from usual real numbers. Okay. All right. So what we're going to do in this lecture particularly is think about methods for finding the inverse. Of course, today everybody would use a computer. You'll have a computation package. It's easy to find inverse, but in the exam, you get asked small matrices and how to find inverse, etc. It's a basic trick that you should know how to do, and it also gives you some idea about some ideas on the concepts behind it. Okay. So what we'll see now is what's called the elimination method. I'll go through it a little bit fast. Okay, we've seen elimination before. Later on, towards the end, we may also, not in this lecture, but much later, you will also learn something called the cofactor method for finding the inverse. Okay, so let's get started. So here is finding inverse by elimination. I'm going to do it with an example. It's very simple. The method is very easy and elegant. For small cases, one can easily implement it. Okay. So what you do is you take 1, 2, 3, 4, the matrix that you have A, and then add on to the right the identity matrix. So notice what I'm doing. I'm just this is just a line. I put a line in the middle, and then I put an identity 1, 0, 0, 1. That's all I'm doing here. Okay. And then what do? This is the left hand side. I'm going to call this the left hand side. I'm going to call this the right hand side. So I'm going to eliminate the matrix on the left and try and make it the identity. And I'm allowed to do row combinations and I'm allowed to do row swaps. Okay, so you don't do other things. You don't need to do other things. So you do these things and then try and get the identity matrix. Okay. So if you cannot get the identity, then the matrix is not invertible. If you get stuck somewhere and you can't find a pivot just by row swaps and row combinations, then it means that the matrix is not invertible. You've seen this, so it works. When it is invertible, this alone works. Okay, so that's what you get here. And here is, so what do you do with the right hand side, right? So in all this I could have done without anything on the left hand side. So what do you do with the right hand side? This is where the trick is. Every operation you do on the left hand side, you have to repeat on the right hand side also. Just think of this whole matrix as one whole quantity. You only do operation on the left hand side to make it identity, but then repeat it for the entire matrix. Repeat it for the right hand side also. I'll show you some examples. You'll see what I mean. For this example itself, we'll see what I mean. Okay, so here is what we do. So how do you make this identity? Here is my pivot. I have my first pivot. I have to make everything below the pivot 0. So this 3 has to become 0. So what do? I make R2 as R2 minus 3 into R1. Okay, this is the first step. So I get this guy. Okay, you can check. I've done R2, replaced it with R2 minus 3 into R1. So notice the right hand side has become something else now. Okay, so this is normal. Just keep it like that. The left hand side is going towards identity, right? It's become 1, 0. The first column is okay. And then you move on to the second pivot. Second pivot is minus 2 here, right? So you find the pivot. This minus 2 is your pivot. Okay. So how do you do with minus 2? I'm going to divide by minus 2, right? So I'll make this 1. So R2 is R2 divided by minus 2. So you get this 3 by 2 minus 1 by 2 and all that. But then it becomes 1. Now it has become closer to identity. 1, 1, 0. Now I have to get rid of this 2. How do I get rid of this 2 by elimination? I'm going to do R1 as R1 minus 2 into R2. So this way if you do, this 2 also is gone. And then you get 1, 0, 0, 1. I've made the left part identity, which means this matrix is invertible. And then here I got minus 2, 1, 3 by 2, minus 1 by 2. You can see here, this minus 2 into this 1 minus 3 minus 2. 0 minus 2 into minus half, and that's just 1. Okay, so you see this becomes this. So what did we do right now, right? So I've been just doing elimination blindly to make this identity. So if you make this identity, what you have left on the right hand side becomes the inverse. Okay, so this is the end of the process. You started with this, augmented the identity on the right hand side, and then reduced the left hand side to identity. Whatever you have on the right hand side becomes the inverse. Okay, so you can think about why this works. I'm not going to prove it to you, but it's reasonable, right? So you can see when I do this, I'm just trying to solve for ax equals 1, 0 and then ax equals 0, 1, and the same thing I'm doing here. The elimination is exactly the same. So if I got it to identity, then it just becomes the same solution. So these two become the solutions of those equations. So that's how this works. So this little process of finding inverse by elimination, very simple, works very easily for 2 by 2 and 3 by 3, for instance. Okay, so I hope this operation is clear. It's a very simple operation. You might have seen it earlier, but just repeating it to say, for small cases, you can find inverse quite easily. So in fact, if you repeat it for an arbitrary invertible ABCD matrix, you will see that the inverse works out to something like this. A lot of people try to remember this. So you see DA and then minus B minus C and then 1 by AD minus B. So later on, we'll see another way to sort of remember this formula, but this you can do in general. So this is the general inverse for a 2 by 2 matrix ABC. Okay, so I hope this operation is reasonably clear. Okay. Next, let's quickly do a 3 by 3 example. I don't want to waste too much time doing this, but anyway, I mean, let's just see what to do. I'm going to augment it with the identity, and then R1 and R2 I have to swap to get a non-zero pivot up below, and then I've already got a 1 0 0 1. This 2 alone I have to get rid of, so R3 is R3 minus 2 R2. I'm simultaneously, dividing by minus 5 to make sure that this final guy is also 1. I mean, this is just a quick way in which you can do this. So if you do this, I get 1 1 1 on the diagonal, and then you got a 2 and a 1 here, and then I get rid of R1, that makes it 0, and then R2, this makes it 0. I ended up with identity, and I've got my inverse. So this is my inverse. You can check. So anytime you get an inverse, you should check A inverse times A. You should check that it becomes identity. You can check in this case also it's true. Okay, so it's a quick process. I hope you see how easy it is to go through this and then finish it off. So if you don't make silly mistakes, you will end up with the inverse correctly. You can multiply with A and check that you will get identity. Okay, so here are some nice special cases. Here is a matrix A. What is special about this matrix, you may wonder? The matrix has only 1 as a non-zero element, and if you see, every row has only a single 1. Okay, the first row has only 1 1, second row has only a single 1, third row also has a single 1. Likewise, every column also has a single 1. Okay, there is 1 here, there's a 1 here, there's a 1 here. So these kind of matrices are called permutation matrices. These are special matrices. In fact, if you take this matrix, multiply by x1, x2, x3, you will get a permutation of x1, x2, x3. You'll in fact get x2, x3, x1. Okay, so it's a permutation. So any matrix which has only a single 1 in every row and a single 1 in every column becomes a permutation matrix. Okay, so what about inverse of a permutation matrix? Okay, so in fact, if you do an inverse of this, you'll get something very interesting. You'll only do swaps, right? So you won't do anything other than a swap, right? Only swaps you will do. So because you're doing only swaps, what you end up getting as the inverse will also be a permutation matrix. Okay, you can prove it very rigorously, but it's easy to prove, right? So you have a permutation matrix, you augmented the identity, and you notice because every row and every column has only a single 1, the only thing you have to do is swap. You do swaps to get it to identity. I've not shown you fully. Here you have to swap the R2 and R3 again, and this becomes identity. I've not shown that, and the inverse becomes something. So inverse will also only be swaps of this, which means it will be a permutation matrix. Isn't it? Think that through. So what you get is a very nice and interesting identity. The inverse of a permutation matrix is a permutation matrix. It's a nice thing to sort of know. If you permute, the only thing you're doing in the operation is permuting the positions of the coordinates. Of course, you can undo the permutation, no? Which will also be a permutation. So that's sort of like the easy way to see this. Okay. So here is this next case. So what kind of a matrix is this? 1 1 1 2 1. So this is an upper triangular matrix, right? So I don't have anything in the lower triangular part. It's all 0. I have an upper triangular matrix. So now if you see, you will only do one type of operation. You will never do anything with the lower part, right? You will not do anything to cancel these parts because they're already cancelled. It's all 0. So you'll only do this part, and if you do only this part, only this top part will become non-zero here. Nothing else will become non-zero anywhere. So if you finally end up, you'll see the inverse of a upper triangular matrix is upper triangle. Okay, so notice how a simple process for coming up with the inverse gives you all these nice results. So I showed it for 3 by 3 and for one specific example. I hope you see the underlying principle here. It's generally true. Any upper triangular matrix, if you invert, you should get an upper triangular matrix. The same thing you can do for lower triangle. I'm not going to go through again. Again, you'll see it's only lower triangular, so I'll only be doing operations from below, and then only the lower part will be affected on my identity part to start with also. So these are easy things to prove. So you can see how our process for generating the inverse gives us nice results like this. Permutation is permutation, inverse of permutation is permutation, inverse of triangular matrices, the same type of triangular matrix again. Okay. Okay, so next sort of relationship which is very interesting in terms of inverse is this connection between what happens between inverse, transpose, product and all that. So particularly when you do product, see when you have inverses you're also doing algebra, right? So you're multiplying matrices and then you may take inverse. You may invert and then multiply, right? So what is the connection is what we're going to see here. Okay, first thing is if A and B are invertible, then AB and BA are also invertible. The proof is very, very simple. The linear transformation is 1 to 1. So of course, we multiply two things together. Again, it remains 1 to 1. So they are invertible. Okay, and here is the most interesting property. AB, after you multiply, if you take inverse, it's the same as doing B inverse multiplied by A inverse. Okay, I'm trying to highlight that just to show you that it's a very important result. So AB whole inverse is B inverse A inverse. So this again is important because this matrix multiplication is not commutative, so you have to be very careful when you do this inverse. When you do AB inverse, it becomes B inverse A inverse. Why is that? You can show why that is true. AB times B inverse A inverse, matrix multiplication is associative, so you can remove the bracket and put the brackets whichever way you want. So if you bracket B and B inverse together, you get I, and then I goes away, and then A and A inverse together, you get I. So AB inverse is B inverse A inverse. But a common mistake is to say AB inverse is A inverse B inverse. So if you see AB times A inverse B inverse, you can't do anything. You'll be stuck, right? So it doesn't give you identity all the time. So this is important. Okay, what about transpose? Transpose also you've seen before, and it's not. It's also very similar in property. AB whole transpose is B transpose A transpose. So this is the standard property of transpose. Sometimes useful when you deal with algebra and transpose together. So let's see a quick proof of this. I'll just give a quick informal argument. If you think of row 1 of AB transpose, the first row of AB transpose, it's the same as the first column of AB. Right? So row and column I'm interchanging. So I'm going to first column of AB. And first column of AB is A multiplied by first column of B. Right? So that's the first column of AB, isn't it? So now I'll go to row. I'll make it equivalent. It's equivalent to row 1 of B transpose multiplying A transpose. I've just taken transpose here, so you get the same thing. What is row 1 of B transpose multiplying A transpose? Is the row 1 of B transpose A transpose. Okay, so you can change 1 to 2 and you'll get the same thing. You can change 2 to 3, you'll get the same thing. 4, 5, etc. Any general row I, it works. And this gives you the proof. It's a simple proof, so you can see it's true. So both inverse and transpose that have this nice property that when you do AB inverse, you get B inverse A inverse. AB transpose, you get B transpose A transpose. Nice property. And how do inverse and transpose play with each other? This is also important. If A is an invertible matrix, A transpose inverse is the same as A inverse transpose. Okay, so you can either transpose first or invert. Either way, you will get the same answer. Okay, so why it's quite easy to see. If you multiply A transpose with A inverse transpose, you get the same as A inverse A transpose. How do I get that? So this is the AB transpose formula, right? So A inverse A whole transpose is the same as A transpose times A inverse transpose, right? But what is A inverse A? I'm using this formula here, right? So this guy, this formula is what I'm using. So think of A inverse A transpose. You'll get A transpose times A inverse transpose. The second guy comes first, okay? So now this A inverse A is nothing but I. So you'll get I here. I and I transpose are the same, so you get I. So A transpose A inverse transpose is the same as A transpose inverse, and you get I. Okay, so it's a quick proof. So you need not be afraid now of algebra where inverse shows up, transpose shows up, product shows up. You can use these rules and simplify some of these algebra. Okay. Okay. So let me stop here, and in the next small lecture, I'll do a few quick problems to show you how all these things play together.